All right, guys, our people, let's call the meeting to order. It is now 7:00 on the second Tuesday. Welcome everyone to the McKinney Amateur Radio Club monthly meeting. For those that have not either done the sign-in sheet or checked in online, you can still check in online. The code is 5Y. 5Y. So for those that have gotten your 50/50 tickets, thank you. During the break, feel free to come up, buy more. We do have some door prizes tonight. Got some pretty nice ones, really. For those that read the newsletter, you probably saw that we've got Dr. Ed Fong's going to be doing a presentation tonight. One of our door prizes is one of Dr. Fong's prized antennas. Yeah. Next door prize is a customized ammo can provided by our very own newsletter editor, Roy. And while it has his call sign and everything on it, he is committed that whoever wins this, he will peel his call sign off and put yours on. Oh, we got another one. Oh, geez, that's heavy. Oh, my goodness. Yeah. And then we have a box of vacuum tubes for folks that like playing tube. All tested and known good. Very cool. So let's put that somewhere where it's not going to fall and break anything. So we're doing really good on door prizes. Let's go ahead and do the Pledge of Allegiance. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. All right, thanks. All right, we're gonna start out welcoming all of our guests. Do we have any guests here tonight? I know of one. It's Patricia. And did you get your call sign yet? Kilo India 5 Zulu Uniform Papa. Well, welcome. We're glad you took time to join us. Okay, do we have, and she's a new licensee as well, by the way. So did we have anybody that got a new call sign in the last month? Anybody that got an upgrade? Come on, people. Is everybody in this room an extra? But speaking of examinations, Alan, our VE coordinator, reported that at the herd this past month, we had 7 examinees. 5 of them passed what they came for. The other 2 going to have to try again. But still, it's good. We wound up with 5 new technician licensees out of that exam session, so that's a good thing. And do we have it? We do. So without further ado, I'm going to let Larry introduce our presenter.
Ladies and gentlemen, I have the distinct pleasure of introducing Dr. Edison Fong. And I believe some of you have seen him come through here before and purchase some of his antennas. And tonight he's going to be telling us all about how they work and how he puts them together and his organization. Thank you so much for joining us tonight, Dr. Fong.
You should be able to hear me. Hear me?
Yes, sir.
Okay, good. Okay, thank you very much. Let's see, I'm going to bring up the slide and then later you have to give me the share screen ability and then we'll get going here. Thank you very much. Let's see, let me bring up the talk here. Okay, now I think the next thing you need to do is Have you allowed me to share the screen? Hang on, where's my, oops. Hang on, am I still here? Hello? My Zoom is gone? Oh, here.
Did you,
I got
are
all
you
these
able to
windows.
see the sharing icon?
Okay, so now I've got to share. Ah, yes. I think we got it. And then if I do this,
There it is. We got it.
like, there. You see the screen, right? Do you see a full screen of the first slide? Uh-oh.
Yes, we sure do.
Okay, good. Okay, very good. Let's get started then. Again, thanks for inviting me. Hey, is it hot over there today? Larry, are you guys still on? I'm not getting any response. Am I working here? Is it working? Can somebody confirm or audio?
Yes, we can hear you. It's brutally hot down here.
Oh, like over 110?
No, it's like maybe brutal was a bit of hyperbole. It's really hot.
Over 100?
Yes.
Oh, wow.
Yeah,
Now,
we're going to be, we've been over 100 for probably the last 2.5 weeks, and they're predicting probably another 2 to 2.5.
Oh, gee. No, because where are you located exactly?
We're located about 35 miles north of Dallas.
Oh, okay. Okay. Yeah, it'll be hot there. My address is 620 Terreal Avenue in Dallas, Texas, when I lived there. But I was at Texas A&M. Oh, I was back in 79 in the summer. It was hot. Oh, it was hot. Let me tell you, it was brutally hot to me. And now here it gets hotter now. Okay, so let's begin this. We're not bad here. We're about maybe 75 right now, but it got into the 80s today. So again, thank you very much for inviting me. We're going to talk about antennas today. And I think some of you have our antennas. The one I'm going to talk about, this is the first of a series of talks. I give like 4, it's expanding now, about 5 talks now, various talks about antennas and radios and things like that. This is typically the first one that people hear about. Some of the stuff I teach at the UC Santa Cruz, more mathematically, but we'll try to make it as non-mathematical as possible. Anyway, we're going to talk about how do you make a standard J-pole dual band? Because typical ones are single band. How do you do it correctly? We did this design about 20 years ago, published in QST, and now it's in a lot of the books. It's in the handbook, it's in the compendiums, it's in Antenna Classics. So it's a pretty standard accepted design now that it does work. People have tested it. The ARRL must have 3 or 4 versions of these things there, and they've tested, yeah, the concept works, and it's fairly straightforward. It isn't real difficult to understand. And here are the articles. The right one was the original one back in 2003. The left one was a roll-up version of it. The roll-up version is one of my students suggested it. Says, hey, can you ever make this into a roll-up version? It'd be really cool to take it camping, put it in a little Ziploc bag and nice and portable. And yeah, so we did that, and the thing only weighs what, 4 or 5 ounces with a thin cable. And then later on, back in 2017, was a big request. Could you make this thing tri-band? Mainly from FEMA. FEMA wanted a tri-band antenna that was fairly small. They had talked to me and said, can you make a fairly small antenna? No radials, 2 meters, 220, 440. And this is the results of that. And that's a talk I give. How do you add 220 to it without affecting the other bands? And picture my daughter there. She has a master's in both masters and bachelor's and master's in mechanical engineering, and also one in electrical engineering. So that was taken the year she graduated from high school, I think. But yeah, now she's a lot older. And we also have had to patent some of our antennas, and it wasn't by my choice, by the way. I had never thought about patenting ham stuff, but we had to when people started copying it. People started selling our copies and even using my name. They weren't claiming that it was from me. They were just saying, this is the Ed Fong antenna when we published in QST and started selling them on eBay. And that's when I had to put a stop to it because some of the antennas we bought, they just weren't made very well, giving me a bad name. Because the design does work very well, but you have to know what you're doing. You have to use a network analyzer. You just can't copy the dimensions. The dimensions are kind of a suggestion because depending on the material you make it out of, the velocity factors will be slightly different. In other words, a quarter wavelength in air is not a quarter wavelength in, for example, coaxial cable, because the speed of light travels slower to coaxial cable, and you've got to adjust for that. So people would just take my dimensions, or some folks took my dimensions and made the antenna start selling it. And so we started buying some of these, and some were resonating at 150, some were even resonating at 160, some were really low because they just took the dimensions. You really have to have a good network analyzer to measure the characteristics of the material you're actually using, because it's not an air. So to make a dual band antenna, I chose a J-pole as opposed to a ground plane. When I was in high school back, 40 years ago. By the way, I've got the title now of the oldest active faculty member at UC Santa Cruz. I don't know whether that's an honor or if you're trying to tell me something. Doesn't bother me. I mean, I'm still teaching. In fact, tonight I canceled a lab class to teach this, but I'm going to make it up for them Thursday. I drive, I teach, I go out field day. I'm a field day chairman. I do all kinds. It doesn't bother me yet, but it will eventually. Anyway, I chose a ground plane. Didn't choose a ground plane because I used to play around with ground planes a lot, and they worked okay. As far as I was concerned, back when I was, a teenager, you build a little 2-meter ground plane, you hit the repeater, you're happy. But as time went on, it turns out the ground plane antenna is not the ideal antenna, and this is why you don't see them that often anymore. A J-pole is a much better configuration, much more ideal dipole pattern, and it's end-fed. Being end-fed is just really, really convenient, as opposed to a radio sticking out. I think I have a picture here. Here's an interesting picture of Sutro Tower, San Francisco. See all that nice, cool fog rolling in. I was raised in the city, but I'm about 40 miles south of there now. But I went up there 3-4 years ago and looked at one of the major towers on Mount Sutro. And you notice, I wish I would have taken a picture of this 30-40 years ago on the same tower. The tower has not changed, but the antennas have. You notice there's no radios? None of these have radios anymore, which suggests that they've gone to more of a J-pole design, which I'll introduce today. And the nice thing about the J-pole design, as you will see, is no radios, which is great because radios will break whenever they're horizontal like that. The force pushing it down when there's winds, they just don't last long. I mean, initially it works, but again, these places get in the winter 50, 60, 70 mile per hour winds. They just won't hold up. And I'll give you an easy example of this. You can see it on the video here. Hang on, got the here. Here. Yeah, suppose I have a vertical antenna like this. A vertical antenna, just assume it's in a PVC pipe, assume it's the vertical antenna. I can hold it up pretty easily like this. The same thing on top of a mountaintop. Doesn't take much to hold it up like this, but it takes a lot to hold it up like that. Right? Because you get gravity pulling it down, what's called R cross F to you mechanical engineers. It's a lot more force. And over the years, that will just fall off. So as you can see on Sutro Tower now, and even if you go up in your commercial towers now, most have eliminated the radio type design. And I'll tell you something else. Did I ever mention it? No, I'll mention it later. See, like a dipole design, that's a vertical. We don't see that very often. We used to build these. We used to build a little arrays, 4-element arrays to get some gain out of our 2-meter repeater. These don't hold up very well. You've got to practically weld it. You cannot make it out of copper pipe because that's just solder at that point. And this thing is way out there. I mean, it works better if this is further away from your mass because the mass disturbs the radiation patterns. He said, okay, let's push it out. But you can't. There's a limit because of the force or the torque that you put at that point. And it's just solder. Solder is very soft. This thing just comes right off after a few windstorms. It pulls right off. The solder cracks and it pulls right off. And plus, this thing with this, so this is just dipole, the upper quarter wave and the lower quarter wave at 2 meters. In the way you feed it, you got to feed it at right angles. It's just really a hassle. I mean, ideally, if you could feed it here, the 50-watt transmitter right there, you're okay, but you can't. You need coax. So coax is right angles, which means you have to have an arm coming out. It's not very practical. Let's see what else I have. Oh, so I like the J-pole. I like the J-pole, and I got introduced 30 years ago by Denny Monticelli 86C. And when I played around with it, it really works quite well for what it is. He gave it to me in just a twin lead, 300 ohm Radio Shack twin lead. I was pretty impressed with just being that simple. And so I figured, well, boy, you can make a base station antenna by putting it into this new durable PVC pipe and put an end connector on it. Sure enough, it works fine. And there's this new sprinkler pipe they claim, and I have no reason to doubt them, that it's pretty much UV protected. It should last for years in the sun. It doesn't fall apart. I remember the old stuff I used to use. Turns yellow after a few years and then it cracks. Not the new stuff is very durable. Let's see. I'll show you here. Here's a basic J-pole design. I'm sure a lot of you folks have made it. Oh, by the way, let's save your questions in the end. It's just easier that way. Do me a favor and jot it down on a piece of paper. Now I can take questions in the end. Live, you can take questions, when you're live, when I'm presenting live, but Zoom is kind of difficult. Kind of breaks my mind the train of thought. Anyway, here's a twin lead J-pole, which I'm sure a lot of you folks have built. You get some 300 ohm twin lead. You do a half wave on top, which is about 38 inches, depending on where you resonate at. So quarter wave would be about 18, 19 inches. See, so in a normal dipole, as I showed you in the previous slide, you would feed it in the middle. But physically, that's really difficult to do. It just wouldn't hold up. Rather, you want it end fed, halfway if you want it end fed. And let me show you how you end feed it. So, well, let's just talk about this single band version. You end feed it. If some of you guys, your extra class guys, will know the Smith chart, I think technicians would not be familiar with it. So if you don't understand, it's just accept it as truth. Here's a Smith chart. And what the Smith chart tells you, it says, if I start out with a short circuit, and I move in a transmission line, a quarter wave from that short circuit. So at 2 meters, it would be 17, 18 inches in the air. At UHF, it would be more like 5 or 6 inches. If it's inside coax, it'll be a little bit shorter. Where does that come from? Where does that 18, 19 inches comes from? It comes from a very basic formula in antenna design. C is equal to F lambda. Let me explain what that is. The speed of light is always equal to the frequency times the wavelength. So if you put in the speed of light, which is about 3 times 10 to the 8th meters a second, equals a frequency, let's say 146 megahertz or 2 meters. The wavelength of that will be 2 meters. That's where that 2 comes from. But now, if you were to use, that's an air, if you were to use coax, in coax, obviously the speed of light is no longer 3 times 10 to the 8th meters a second. It's got to be slower, right? Nothing speeds up the speed of light. When you put a wave through coax, it loses about 20% of the speed. So you cannot use 3 times 10 to the 8th meters a second. You use about 2.6 or something, 2.7. Then you'll find that equals F lambda. The speed of light is always equal to frequency times the wavelength. The frequency stays the same, right? 2 meters, 146 megahertz. Then what will change is the lambda. So the equivalent wavelength in a piece of coax or twin lead is not 18 or 19 inches anymore. It's more like 15 inches, 16 inches, depending on the exact material you use. So what's important is that here's if you have a short circuit in a transmission line, for example, UHF, which is about 4.5, 5 inches. If you go 4.5, 5 inches, it will be an open circuit. And that's hard to believe, that's not intuitive. Let me get you a stub here. I have some quarter wave stubs here. I'll plug it in. I thought they were somewhere. Here they are. Yeah, look, for example, a quarter wave stub at UHF, although 6 inches in air in RG58, for example, in RG58, that's actually only about 5 inches, maybe a little less, 5 inches. That's a quarter wave stub. So you would think, I'd fool a lot of my students there. I say, what is this open circuit? It's not, I don't know if it's an open circuit, but I haven't shown it. So what is it on this end? Most people say open circuit. At DC, it's an open circuit, not at AC. In fact, at UHF, in this case, it will be infinity. So the way I teach this typically in my classes, you got to, especially when they're just new grad students that want to learn radio, non-hams, which, by the way, in my opinion, if you want to learn radio and you're not a ham and you're a graduate school, it's because you're probably fairly smart. You looked it up. How do I make good money here? I become a radio engineer. You probably won't make a very good radio engineer, because I think to do it for a living, you have to really like this stuff. You would have been a ham by then. So I notice this, when I get amateur radio operators in my grad students, oh, they're all much better. The ones that are non-hams just don't catch on. And I try to teach them the intuition. For example, we know like a block of wood, right? A block of wood, is it a conductor or is it an insulator? Well, it's an insulator. At DC, it is. Of course, it's an insulator. But at AC or at radio waves, well, it's a conductor. Well, how do you know it's a conductor? Well, if you take your radio, right, your cell phone order, when you walk inside a wooden building or even a cement building, you still get a signal. That's because the signal's going right through. But DC wouldn't go through that. And also another good example is this, aluminum foil. Take aluminum foil. You ask someone, is that a conductor or is that an insulator? Well, most people say it's a conductor. That's absolutely correct at DC. But clearly it's not a conductor at AC or RF signals. It's a shield. So it stops waves. So you got to keep those in mind. That's the simplest way to keep it in mind. Insulators at DC are conductors at radio waves, and conductors at DC become shields. So that's a good way to keep it in mind. So again, an open circuit, similarly, an open circuit on one end, which is infinity, right? If you go a quarter wave, is actually a short circuit. And we try this experiment many, many times with my students just to try to break this idea that an open circuit is not open, physically open. That's DC. And AC, it could be a short circuit depending on the frequency. So that's how a J-pole, how we get to take advantage of that. In a J-pole, the center is 70 ohms or so. That's why you can feed it with coax. But the end is not. The end's where the antenna radiates. It's a very high voltage, low current, which means high impedance, right? Ohm's law says Z is equal to B over I. So the impedance must be very high at the end. So how do you feed it? You need a high impedance at that point, a high impedance to feed that piece, because it's only low impedance in the middle, so you can feed it with coax. But then you can't feed it with coax. You need a transformer. And what do? You get a quarter wave piece. In the case of 2 meters, it would be about 16 and a half, 15 and a quarter plus 1 1/4, about 16 and a half inches. Remember, it won't be 18 or 19 because it's in the twin lead. They'll slow down the speed of light by 15, 20%. So it's shorter. So 2 meters in twin lead is about 16 and a half inches, not 19. But if I short the end, just like in the Smith chart, if I take the short circuit, move a quarter wave. Well, I'm moving a quarter wave, which is about 16 and a half inches. That's a high impedance. Then it matches. High impedance, and that's how it works. And then where do you tap it off? Well, if that's 0 ohms and if that's infinity, got to be 50 somewhere, right? This thing isn't discontinuous. And it turns out to be about 1 1/4 inches. And these antennas are very popular. I mean, both industrially and in the ham market. They're easy to make and they work well. In fact, they work about 1.6 dB better than a ground plane. And I'll explain that later why. So that's how basically a J-pole works. Now, this is sort of 2 meters. So back in the, I guess early 2000s, they were having all these HTs and mobile rigs were becoming all dual band. They were becoming all dual band. And they were cheap, right? If you're going to buy a 2 meter radio, you might as well get UHF with it for an extra $50. Next, handy talkie, they were just phasing out all the single band stuff. But how about antennas? That's where we came up with this dual band idea, because a lot of the guys in the swap meet said, hey, I bought this dual band handheld, but I need a good antenna and I don't want to pay another $100, $150 for it. So what folks did notice is that their antennas, their J-poles, their ground planes, sort of worked at UHF. They would, the first thing hams do is they put it through a SWR meter. If the SWR meter is low, it must be good. Not necessarily. Right? I give you a dummy load and the SWR is low. Doesn't mean the antenna is good. Well, folks began to notice, yeah, the antenna works, it resonates, but it doesn't work very well. I mean, quickly you would notice it doesn't work very well. And if you notice it, if you say, I'm just using a handy talkie, I notice it doesn't work very well. That's a lot of loss. That means measurable loss is quite a bit. So if you quantify it, that's actually 6 to 8 dBs of loss. If you use a VHF antenna at UHF, you lose about 6 dB. 60, that's 1/4. It's 1/4 of the efficiency of a quarter wave ground plane. That's a lot. That's why you notice it. That's why it's insignificant. So significant, not insignificant. So these friends of mine saying, hey, Ed, you think you're a smart guy, right? I don't know. I teach. I guess I'm supposed to know antennas because I teach it at the university. Here's a real practical. Can you make the challenge is, can you make a J-pole simple that we can do? Make it dual band and have it perform as a half-wave radiator. See, so I'll give you an example of this. If you simulate this in free space, a good reference is just free space. If you simulate a vertical dipole at free space, and this is this is the sky, Earth, this is sea level right here. The radiation pattern at the fundamental looks like this, the figure 8, well-known figure 8 pattern. And then looking from the sky, it's 360 degrees. So it's really nice. A vertical dipole is really nice because it kind of forms a null at the sky, which is exactly what you don't want energy radiating there anyway. You want it at sea level. So really a vertical dipole, a good vertical dipole is actually a very, very good antenna until you use it at its third harmonic. So its third harmonic, it resonates. It's got a reasonable SWR until you start using it. Why is it so bad? Well, mathematically, the reason why it's bad is because when you use a fundamental antenna at its third harmonic, 75% of it goes into the sky. These big lobes here, right? If you actually were to integrate this, if you know calculus, if you integrate this function, 75% of the area is here and 25% is left here. That's not good. Not if you want to talk to someone, on Earth. Now, a little bit different if you're trying to, my antenna, someone or regular vertical, say, wow, I talked to the International Space Station. They could really hear me on UHF. Of course. If you're operating at a third harmonic, a 2 meter antenna operating at UHF, the energy goes into the sky. But if you're not doing that, that's not good. Only about 25% of the energy is on the ground. So what is it that you can do to make this VHF pattern look like this also at UHF? So that's what I'm going to get into. And the design, the goals had to be simple, reproducible, no radios. Radios is out of the question. Again, you can't put a capacitor in there because you couldn't buy one at UHF. Let's say the simulation says, oh, you need a 5 picofarad cap. Most caps, if you measure it on a good network analyzer, let's say a 6 picofarad is what you can buy, 6 picofarad. It won't be 6 picofarad at UHF. That's like below 30 megahertz. It will have series inductance, series resistance with it. It just wouldn't work. You would not be able to purchase one that would work consistently. And same thing with inductors. You may be able to wind a coil, but you certainly can't go buy an inductor. Let's say 50 nanohenry or something like that. You wouldn't be able to, it would be so lossy at UHF and with parasitic capacitance, it would have probably gone through its self-resonance. So we couldn't use any of this stuff. I figured, that's out. That's not practical. You might be able to make one or two, but it's not practical. So anyway, I tried all types of configurations. And what I'm going to show you is what I came through with, and I think a lot of you folks have these. They work. They really do work. In fact, clubs have tested them. A lot of clubs have tested them. I mean, I know you guys can't do it so hot, but during the fall and during the winter months, a lot of clubs in the Midwest have just tested various antennas, and ours always comes out ahead. And we work on this. And I'll tell you why and why it always comes out ahead. Let me explain this. So here's some typical J poles you guys probably seen. Copper J. We know how one works because antennas are my hobby. We develop sophisticated antennas. The universities are satellites and all this, but this is like really cool stuff you can talk to the ham clubs about, because I'm still ham at heart. So we build these, my students, but I'll show you. I like to show them, you can always build an antenna, and then they love to build this stuff and measure it. And so we build them. This is the typical copper J, which I'm sure there's thousands, tens of thousands of these out there. The reason why you would not want to build one unless you've got extra coppers, well, that's about $40 worth of copper now. These elbows, these T's and the end caps, pretty expensive. Our antenna is a lot cheaper and same performance. Now, one thing about the antenna to note on this copper J is it doesn't perform well at UHF. And you say, well, why not? I thought you said any antenna that works at VHF will also work at UHF. It should with the 6 dB gain or 6 dB loss. This is actually worse. The reason why we found this, here's that half wave that I discussed. And here's that transmission line match. Right? Here's the short circuit. And here's how you tap it. We zoomed in here. Here's how you tap it. Well, it does, the design doesn't scale. By the time you get to UHF, right, it's only 5 inches or so. That jump, that big jump, and what determines that distance of that jump? It's that T and that elbow. It comes up like, I think, 1 7/8 of an inch, little under 2 inches. You can't expect something to go wrong, right? It's a little under 2 inches. Of course, something's going to go wrong. At UHF, an ideal quarter wave is only 6 inches, 5-6 inches. You cannot lose 2 inches in that. Open, not cover with coax impedance match. It starts radiating. At UHF, this will start radiating. And it would even be okay if it radiated in the right polarity. Now it's horizontally polarized. Yeah, even the wrong polarization is radiating. And then even whatever wave gets into this transmission line is not very good anymore. The spacing's too wide again. At VHF, remember VHF, a quarter wave's 18 inches. At UHF, it's only 5 to 6 inches. This is no longer, it doesn't scale. This is no longer a good transmission line at UHF. So it just kind of gets lost. What we notice is the SWR is pretty bad. And you guys probably notice this on this configuration of UHF. And it just kind of radiates all over the place. If you're working a repeater, you probably hit the repeater. But if you measure it, does not perform very well at UHF. VHF is still acceptable. Again, I wouldn't build it because the copper is very expensive and it kind of looks bad. I think this sticking on top of your roof, your neighbors might wonder what that is. Well, if it's a straight PVC pipe, you can tell them that's a flagpole. And it would pass. But again, this would not work very well at UHF, although we've tested these at VHF, they're not bad. I don't think it's comparable to ours, but it's not bad. Okay. And another configuration that's kind of worth discussing. Oh, my wife is talking on the phone outside the yard. This is the arrow. The arrow antenna is pretty cool. And again, we didn't build one, but I bought it. It wasn't worth building. Pretty hard to build. This one, the arrow. It was, $50, you just buy it and you just test it out. But how does it work? It's pretty interesting how it works. It's a J pole. Here's a standard J pole, a half wave, a quarter wave, and the spacing is pretty far, but surprisingly, it still works okay. But at UHF, what they do is they put an extra element here. So the way this actually works at UHF, this forms at the UHF J pole. And at VHF, this forms the VHF J pole. And they kind of parallel. It's pretty easily done if you see it. They're paralleled in the same resonance. So it's only one connector. What's the problem with this? Well, it's an interesting solution. So the UHF is working right. Of course, the VHF is working right. So when you stick in a UHF signal, problem is it still sees the low impedance of the UHF signal in the VHF region. It's still the third harmonic. In other words, the VHF antenna still resonates at UHF. It always resonates at their odd harmonics. So what happens when we measure this, half the power that you put in here, if it's a UHF signal, goes into the proper antenna. The other half goes into the improper antenna. In the improper antenna, you lose about 75% of your energy. So it's an improvement. But it certainly doesn't compete against ours where we actually totally decouple it. What you really need is something that totally decouples the UHF. So that's one. And then some people mention the Slim Jim. I only mention it here because the Slim Jim is just the J pole I showed you at first. But someone came up, when you tie the tops together, you get 6 dB gain. I just want to tell you, no, you do not get 6 dB gain. It's just all the same. We've measured it, simulated, it's all the same stuff. Larry Seebeck, who passed away a few years ago, he had a website about this saying, I don't know where this came about, it gives 6 dB gain, but it does not. Now, I do give a talk on how to get about 5 dB gain out of a J pole. That's a collinear. And I can explain that in another talk, but it's much more elaborate than this, much more elaborate than this. It's not, in life, there's very few things that simple. Oh, short these 2 wires together and you get 6 dB. You tend to be suspicious. Even if you don't know E and M, you would be suspicious. So let's see. So let's get into what I did here. Okay, here is the J pole. Let me show you here our solution. And first of all, before I show the solution, here's the quarter wave voltage plot. When you have transmitting a carrier, the voltage plot along this quarter wave stub is obviously, when there's a short circuit down here, it's going to be 0 volts, high current, low voltage. As you get up to a quarter wave, remember, a quarter wave is high impedance. So that means it's high voltage, low current. And that's exactly, if you measure with the RF voltmeter, you get no voltage here. As you go up the line, the voltage goes up, and it's going to be the peak at a quarter wave. And of course, high voltage, low current, that means high impedance. High impedance and matches to the antenna. And if it's a half wave here at 2 meters, it would be great. And that's typically what you do here. It's a half wave. But now, how did we do the UHF portion? So if you add up 17 inches, 4 1/4, 11 1/4, it's about halfway for VHF. So now what happens at UHF? So the VHF portion works. What happens at UHF? Well, what happens at UHF here is the wave. Let me show you the wave that happens in the stub here. So if you take an RF voltmeter and feed a UHF signal in here, it will look like this. Obviously, at the short circuit, it's 0. And right at about 5 inches, it starts reaching a peak. But it doesn't continue. That's a quarter wave. A quarter wave up here. Then another quarter wave, it starts reaching a minimum, another quarter wave. So half wave back, half wave up the stub, it reaches the 0 again. And then if you continue, you'll get back a peak. So it does wind up a peak at the same spot, out of phase, but it doesn't matter. The phase doesn't matter in this case. The phase is still a peak, which means it will match this point. What the problem is, when it matches that point, what it would like to see, your antenna, is about 11 or 12 inches, depending on the frequency, 11 or 12 inches. It doesn't want to see, 36 inches. Because what happens at 36 inches? So if you go back to the slide, so what happens here? So it's 37, 36, 37, 38 inches or so, halfway. It reaches a peak. It would like to see about 11 or 12 inches, but it doesn't. It goes here, it sees a half wave, and the signal moves on. it would have liked to stop. If it stopped, you would get a nice waveform. But the signal moves on. That's where you get those lobes intuitively without the math. That's where those lobes come in. The current kept on continuing, but it really wanted to stop. And that's when you get what we call the 4-leaf clover pattern. So what we did here was, how about let's take that quarter wave stub principle again. If I take a piece of coax like this, if I short it on one end, that's 0 ohm, short it, you short it on one end, and it's about a 4 1/4, 4.5 inch at the other end, it's an open circuit. It's a quarter wave, according to the Smith chart. And a short circuit, a quarter wave up, would be an open circuit. So at UHF only, because there's a short here, you will see an open circuit there. May not be infinity, but pretty high, several thousand ohms equivalently. What that does is it stops that UHF signal. You had a beautiful match here, you had a beautiful match here with an extra half wave delay. What it would like to have seen is 11 or 12 inches. And electrically, that's what it'll do, because it's a short here, it'll be an open circuit there. What happens at VHF? At VHF, that doesn't resonate. It doesn't resonate. It's just basically a wire going through with a kind of like a capacitor out here. Doesn't do much. Therefore, at VHF with this signal here, it sees 11 1/4, 4 1/4, and 17. I think that adds up like close to 38, 39 inches. That's basically how it works. And then you can make a roll-up version of this. We just have coax with BNC. The trick is, can you do it all in one twin lead and then put heat shrinkable tubing around it to have it all hold? And you can. With a little bit of effort, you can. Now, what I do want to point out is, you notice this piece here is 16 1/4 plus 1 1/4. That's 17 1/2. 17 1/2 here. This is going to operate in air, not in a PVC pipe. The PVC pipe, again, slows down the wave by about, almost 5%. Oh, not quite, 3 to 5%, depending on the pipe. 3 to 5%. So that means when you stick this antenna in a pipe, it's got to be shorter, because C is equal to F lambda. C is equal to F lambda. The speed of light in PVC is slowed down compared to that of air by 4 or 5% in that range. But look at these dimensions here. Here's 16 1/4 plus 1 1/4. That's 17 1/2. But the one that goes into the PVC pipe, this goes in a PVC pipe, so it's protected as a base station, is only 16 1/2. And also here, instead of 17, it's 17 here, but if it's going to operate in air, it's 18 is where it resonates. So it all kind of makes sense, because one's transmitting right into air, the other one's transmitting into a PVC pipe, and you can say, how much loss does the pipe have? RFI is nothing of significance that you can barely measure. It's nothing of significance, but the resonance changes. The resonance changes for sure because of the speed of light. So if you guys have any questions, let's take that later, because that's a concept that, again, I try to get across to my students. One of the things they had a problem with designing antennas in the 60s with satellites going into space. We weren't sure whether we could generate a true vacuum, because as the satellite goes up and the antenna dimensions will change. It no longer has air, because air, it turns out that air, nitrogen and the smog we have and all that, slows down the speed of light by maybe 1, and probably not quite 2%, 1% at least. Okay, so we found that, what time is it? Okay, we found that the pipe, the best pipe to use was the Lowell's 23990. That's class 200. I think any of the class 200s will work. We did find that the schedule 40, the thicker stuff, worked okay, but we could measure some differences because it's just a little too thick. And actually, it's one of my grad students did a very quick experiment. If you're wondering about covering up an antenna with something like a PVC pipe, how much attenuation does it produce? Actually, a pretty simple experiment is take some of that material, 5 or 6 inches of the pipe, stick it in your microwave oven for like 5 minutes. And if it gets warm, that means it's not good, right? That means it absorbed RF. But you'll find that the Lowell's 23990 really doesn't get warm at all. It stays at room temperature, which means it's pretty good. Probably RF goes right through it. It doesn't absorb energy. So, and it's cheap, right? You just go buy it at Lowe's. It's pretty inexpensive. So the bottom line is, does this antenna work? Good question. So when you measure it on a spectrum analyzer, it does work. A 2-meter J-pole at UHF gives this as a reference. And if you use ours, same spot. By the way, this is not some fancy measurement. This is a parking lot 50 yards away. Just make sure you get a good relative measurement like this. And it's in the clear. And this is fairly in the clear. Did it in the weekend. Parking lot was fairly empty. And sure enough, if you use our DBJ1, which is with that little stub, it gains about 6 dBs right there. It gains about 6 dBs. There's no doubt about it. In fact, I got this table because one of my students wanted to understand, how do you measure antenna gain? That's pretty important and very common to measure antenna gain. It's obvious most people don't know how to measure antenna gain because you see these claims of 6 dB here, a Comet Diamond X200. Hey, when it's in our antenna range, basically our antenna performs about the same. So I don't know what kind of dB they're talking about. But the way we measure it, when I looked it up, they say it's to claim a certain gain, you should do 5 measurements on a rainy day, 5 measurements on an overcast, foggy day, and 5 measurements on a sunny day. Makes sense, right? Because those different days will have different velocity factors. If it's a rainy day, the velocity factor, because there's something in between, it slows down the speed of light quite a bit on a rainy day. You guys probably noticed that just the attenuation on a rainy day, right? With UHF. So that's what we did. And this is the average of 15 measurements. And sure enough, the models that we do, and this is EasyNAC, if you have a reference VHF quarter wave mobile antenna minus 24.7 dB, you substitute a rubber duct on it. So this is based on 15 measurements. So I'm pretty confident. It loses about 5-6 dBs. A standard J-pole actually is better, right? Standard J-pole is better than a ground plane. Not by much, 1.5 dB. Noticeable, clearly measurable, not major. And our dual band J-pole, pretty much like that of a standard VHF J-pole, which is good. Now, okay, so this just shows you at VHF. Our claim to fame was UHF, that our antenna performs well at UHF. Okay, so at UHF, again, we use a reference quarter wave mobile, minus 38.8. A rubber duck at UHF does not lose as much. And intuitively, it makes sense because they're about 5 inches, usually 6 inches. That's pretty close to a quarter wave. And then the rest is dependent on your handheld, right? How good of a ground is, because you don't have the extra quarter wave. And, you know, I found some rubber ducks actually perform quite well, but they typically a couple of dBs, 2-3 dBs. But certainly not like a VHF. At VHF, when you start using a rubber duck, it's considerably less than a quarter wave antenna. And intuitively, right, because it's like 5-6 inches and it should be like 18 inches. Here, it should be, they're like 5 or 6 inches and the antenna should be maybe 6 inches. So it's pretty close. It's just the ground, you don't have ground radials. It's just a handy talkies chassis that makes up the other quarter wave. That's why I think that's where most of the losses are. Now, on a VHF J-pole, it should not work at UHF. It resonates, but it doesn't work very well. And sure enough, when you measure it, it's terrible. It's like, again, minus 45 versus 38.8 as your reference. So it's 7-8 dBs off. It's quite a bit off. So again, in an emergency, you can always use a VHF antenna on UHF. Don't expect great performance. Now, if you use that stub, most of the call comes back. It almost is comparable to a quarter wave antenna. A quarter of 38.8, it's about 38.9. Not bad. I mean, it's quite considerably better than using a VHF antenna at UHF. That's minus 45 versus minus 38.9. That's by 6 dB, about 6 dB. It does work. Now, here's our lab. Here's my old lab here. Originally, when we did this antenna, we did it on a 8753 non-microprocessor base analyzer. Really nice unit. Not cheap, though. It's like, like $85,000. These newer ones are PC based. So I've got one here in my house, and we also have one in the lab at school. It's called the 5062. They try to make it look the same in the menu so that you don't get confused. But really, when you open it up, that's a full analyzer, and it's a full color tube. This is just an LCD screen, and it's really just a PC. a PC in here, and then it's the front panel that's all the RF stuff that's in there. But everything's driven by a PC, so you have infinite memory, plotting routines. This one happens when we bought it, runs on Windows 10. It's a Windows 10 machine, not Windows 11. And that means you can change files and all this. It's kind of nice. And it's just cheaper. It's like 48,000. Oh, here. So a lot of people ask, how about that stuff? You know, what did you contribute? You contributed the stuff. So why don't you just put it on one of your analyzers? Here it is. Not infinity. We swept it from 30 megahertz to 1 gig. It's not infinity, but it's high compared to 50 ohms and compared to 0. I didn't expect it to be infinity. It's hard to get infinity at UHF. Same thing as like it's hard to get a short, right? It's very tough. So that's pretty high. I mean, it's not infinity, but it's pretty high. And when I put my hands around it and everything, that resonant point is pretty stable. Everywhere else, where it doesn't resonate, sure, you can't control it, but the resonant point is pretty stable. And then, at 146 megahertz, what does it look like right there? Kind of like an open circuit, very close to it. It's a piece of wire, it looks like that. So see, here it is. Here's the dual band one. You hold it from the bottom and it will last for years. As simple as this antenna is, it's all round. So even when I see 60, 70 mile per hour winds in the winter, we don't get those often, but we do get them. This thing doesn't even bend because it's all round, no radials. It's exactly what you want in an antenna. And then here's our roll up. We sell the roll up version of that. It all rolls up, goes into a baggies or Ziploc pack. And what we do is we include a 6 feet RF extension. These are custom made for us. And it's got a male BNC and a female. So you just plug this into there and then you can extend them. And if you want to buy more, you can buy more. And then we include all the adapters, BNC, SMA male, SMA female for your Baofengs. So this is actually a grad student of mine that came up with this idea. And we sell quite a bit of these for emergencies, for backpacking, camping. It's really, really nice. So if you like this talk, I give another talk on how you get gain out of a collinear, out of a J-pole. That's what most people are using commercially. Also give one on how do you make a tri-band? The tricks of how do you add 220 megahertz to this design I just introduced. Here are some interesting radios I thought that for tri-band people. You don't have to spend very much. These radios are BTEC, Radio Oddity, even the BTEC, there's a Baofeng UV5R ×3. That's the one that also covers 220. I think they sell for like $40 now. It used to be 60. So if you're going to buy a new radio, actually, these are good choices. We give these raffle prizes all the time. They seem to be okay. Okay, so if you guys like, we sell these antennas. That's how I raise money for our group here. Since I'm giving you a seminar, you guys get a pretty good discount. The DBJ1, which is the one I talked about tonight, VHF ham, UHF ham. We also make a commercial version of that. So it covers 152 to 157. So it's part of the Marine band, MERS band, and then GMRS band. Same price, it's a different antenna. So they retail for about $55 on our website and also from our distributors. When you pay the postage, an antenna is about $55. No postage here if you guys order through the club, $35, so it's a good 20% off. The roll-up's the same thing. We include the adapters and the coax. And again, it retails for $55. And if you order through the club, and I'll send Larry a spreadsheet, you guys just fill it out and I'll just send it to you, $35. The tri-band, which I haven't given them talk about, typically it runs at $90 in postage. We'll send it to you for $65, including the postage. We also make a GMRS one, also UHF. We can turn this to UHF. That's the dual band collinear that I give a talk on. How do you get 5 dB gain out of the J-pole configuration? Again, $43. Normally it's $60 in retails. Also extra extensions for our roll-up, $6, and then adapter. A lot of people request a BNC to 259 for the roll-up because this terminates in a BNC. You want to go into a mobile, you need the adapter. But right now, how about questions? I'll take questions now, either from the audience or from Zoom. Come on, guys. Throw me some questions.
I think we've got at least one for you, Dr. Fong. Oh,
Sure,
no,
sure.
we don't.
No, we
Larry,
don't?
what question do you have?
Thank you very much for presenting tonight, Dr. Fong. I do have a question.
Sure.
You were specing the PVC. You gave a Lowe's part number 23990.
Correct.
I'm not familiar with the Lowe's inventory stock. I was wondering, does that translate to a 3/4 inch schedule 40?
Right. 3/4 inch scale to 200. Yeah. Yeah, exactly. It
Great.
sells for about $5 for 10 feet. I mean, $4.60, I think. Yeah, like $4.50 for a 10 feet section.
There you go. Thank you.
So, another interesting thing that I can offer you guys, we have bought a bunch of these. I'm a bro. I don't know, bro. I'm a HF ham. I like CW and I like single sideband. You know what? The greatest thing since sliced bread. I've had so much fun with this radio. Are you guys familiar with this radio here? Any of you guys? It's called the USDX.
No, we're not.
You're not? It is the coolest thing around. It's about the size of a novel. It puts out 5 watts CW. It's the Northern Cal QRP Club has been playing with this design for a long time. But it covers 80 through 10 plus work bands, general coverage receiver. It's all SDR done in a FPGA, all mode, FT8, digital, single sideband CW. It even has a CW decoder. Now, I recommend it comes with a mic, but I really like this one by QRP Kits. This mic works a lot better. But it puts out a little under 10 watts PEP. It uses what's called a Class E amplifier. Really efficient for single sideband. It's really cleverly done using delta sigma modulation. Has a built-in 4 ampere hour battery, a lithium ion with charger. Now, not all of them will have that. You got to make sure you buy it with it. For $155, I think this is one of the greater bargains right now out there. They work great. I mean, it's an SDR radio, so it's got DSP filters in it. It's got CW filters, and if you see it, the reason why I'm mentioning this, we bought a bunch of them. I use this in my class to experiment. And Ron, one of the distributors, purchases these really good price with a 4 ampere hour lithium battery with the charger. It's $155. So if you guys want to buy antennas, if some of you guys want one of these radios, just say, we can send some to you. I don't have infinite amount, but I've got about half a dozen left from these experiments we're doing. But it is a really cool radio. You put an end-fed antenna, go up on a hill, and you really can make pretty good contacts with it. So it's not on this list. It's not an official. But yeah, I ended up this summer, we got about maybe half a dozen left over. Oh, the students love it. It is amazing. Especially, I'm not an FT8 person, but some of them put it on FTAs. Oh, Dr. Fong, man, we talked to Russia last night and all the whole list. I go, but you guys cheated as FT8. Try doing it on phone. So on phone, I've got a pretty good antenna here. I've talked all over the States, all over Canada, Mexico, Hawaii, Alaska. I have not talked to like New Zealand, where my location is. But otherwise, I've gotten all, the winter field day. I talked to all the sections. It's pretty cool. So none of you guys have heard of this.
No, we didn't.
Oh, it's really cool. I mean, again, it weighs less than a pound, like this.
Yeah. What did you say the model number was?
But a USDX Plus. There's several versions.
USDX Plus, everyone.
There's a lot of versions of it because it's the Northern Cal QRP Club that works on this design. And then another group in Germany, Manny works on it with his group, is DL2MAN. And they kind of collaborate. A lot of it's in Python software. It's big. Most of it is programmed in an Atmel FPGA. Not all of it. And then the synthesizer uses a Silicon Lab synthesizer chip.
Very neat.
And of course, the filters are still there. If you open this up, you see all the filters and coils, but everything else is pretty much done in in the IC format. It's pretty cool. I mean, I take it along with me, and wow. And then again at night, I make all kinds of contacts. Now I have a pretty decent antenna, granted, but still pretty lots of fun. But if I go up in the hills and have a dipole, it does really, really well. It's really well thought out.
Nice. I think we've got a couple more questions here.
Yeah. Go ahead. Yeah.
Brand. Hang on a second. He's walking up to the microphone.
Oh, so now I don't see a picture of is there a big crowd there? Or how many people are in the audience?
We've got about 30, 40, no, about 40 people here tonight.
Oh, okay.
Dr. Fong, thank you
Yes.
so much for the enlightening presentation.
Oh, sure.
One of your slides mentioned lightning protection, that the antenna is a DC short.
Yes,
So
yes.
here in the Dallas area, we get a lot of lightning storms. And in the past 3 years, within a 2-mile radius of my house, there's been 3 houses that got struck by lightning, most of them destroyed. Can you talk a little bit more about lightning protection with your antenna?
So I forgot to talk about that. There's no such thing as a lightning arrestor. You know that, right? If you and I can come up with a lightning arrestor, a rule where you arrest lightning, we'll be multi-billionaires. Because there's for example, a lightning arrestor, when you buy one from MFJ or RF Engineering, or what it does is, a typical one is a gas. It's filled with gas that after about 40 volts, it short circuits it. So if your antenna, that's the other thing I don't like about ground planes or dipoles. They're open circuit antennas. DC wise, they're open circuit so they can hold charge. But you notice in the J-pole design, it's a short circuit DC. So it's always discharging the main element. It's a DC short. Now, it doesn't arrest lightning. Your regular antenna doesn't arrest lightning. But what it does do is, if there's a lightning storm close by, and it's millions of volts, you get lightning, it's millions of volts. All you have to do is induce about 30 to 40 volts and you'll burn out your front end. That's what a lightning arrestor does. It shorts out or discharges your antenna. But in a J-pole, where it's a DC short anyway, it's always shorting it out. Now, that's not going to prevent a direct strike. A direct strike is a direct strike. I mean, a direct strike can be an insight. I mean, you hear direct strikes of trees in the forest. It just hits and that's it. There's nothing you can do. I mean, the only thing you can do when a lightning storm does occur and it's hitting close by, disconnect all your radios from it. I would suggest that. But any direct strike, now, if you're in a high lightning area, you should have some lightning poles, right? Discharging poles on top of your roof that go to ground, because then it tends to go towards that more than your antenna. So yeah, a lightning arrestor will not do any good in our antenna. It's already a DC short. And that's not to say it will protect yourself from lightning. It will discharge. During a lightning storm, you will not build up charge on your antenna. And after you build up about 30, 40 volts, most front ends of radios will burn out. That it will prevent. Does that answer your question?
Yep, he nodded his head. Any other questions in the room? All right, Dr. Fong, looks like you've drained the room here.
Yeah, so Larry, let me send you a spreadsheet. Let me just get a show of hands. Who's interested in one of these radios? We have about 6 left because we bought a bunch to do experiments with. Anyone interested? They're $155. That includes the shipping, includes a 4 ampere-hour battery and charger.
Okay, we've got 7 hands in the air here, so
really?
we can all
Okay.
it sounds
Yeah,
like.
I don't know if I can have that many. These are just left over. We had to buy a bunch because the students were doing a bunch of experiments with them on FT8. But maybe I can. We go through a distributor. Maybe, I mean, if there's really interest, I'm sure I can order more from him. It might be a delay.
Okay, so for those of you in the room that are interested in that, get with Larry here. He'll get your information, and we'll try and gather up. And
at most,
we'll figure out how to get it all ordered.
Yeah, I've got about 6 here left over, so I can send those immediately. But if you want any more, I'm sure I can talk to this guy named Ron, the distributor. It's so fun. It's got you don't even have to know CW. It's got a built-in CW decoder, obviously a built-in keyer, compact. I just have lots of fun with it. I mean, and what do I use at home? I mean, I use Collins, Drake equipment, professional, commercial grade stuff. But this is like tiny. It go up the hills here. There's a waterfront here. A bunch of guys have these. They go out and set up their 43 feet vertical antennas. I am amazed. When you're by water, they talk to Japan on 15 meters. So it's pretty cool. Anyway, no more questions. Thanks a lot for having me. And if you enjoy this talk, we have a few more, and just schedule me in. As long as I'm not
fantastic.
I can schedule.
Really appreciate your time. It was very informative. Thank you.
Very good. Very good. Okay, you guys stay cool. That's all I could say. See you later. Okay.
Bye-bye. All right, everybody, let's settle down. Time to get started. Okay, so thank you everybody for settling down. One last bit of field day business. I decided after watching the phenomenal group of people that came together to make field day happen, I have sponsored some ham radio outlet gift certificates to give out to some folks here. So I've got some categories of people. We've got the marathoners, the ones that were there all night, which was Sid, Mike, and Larry. Our network software guru, Mr. Sean. We had our equipment mover and antenna wrangler, David Hampton. My safety apprentice, Roy. We had our construction and assembly anchor person, which was Kiri. And we had our club feeding machine, Mr. Lance. Our teacher operator spaceman of Bran. And our club ambassador of Jerry. Thank you so much for everything everybody did. After the meeting, see me. I've got your gift certificates up here. All right, just a reminder, we have the MARC information net every Sunday night at 8 o'clock on the 2-meter repeater. Please join in. Simplex net is every Monday night at 8:30 p.m. It's on a frequency of 146.54 plus or minus, depending on if somebody else is already camped out there. So just be listening. We do breakfast at Denny's every Saturday morning. People gather at about 7. We've got the waitress. She is perfect. Right at about 7:30, she comes and takes orders. So come on out. We get anywhere from usually 15 to 25 people for breakfast. It's a good gathering. And our next meeting will be in September. Can I have a motion to adjourn? Lewis, pick somebody and write their call sign down for the motion to adjourn. Second is Ron, K1HZ. All in favor? Aye. Any opposed? Good enough. Thanks, everybody. Great meeting.